Welcome to our deep dive into the world of fluid statics.
Yeah.
I think before we get into the specifics, like why are dams shaped the way they are, or, how does a giant ship actually float?
Right.
We got to start with like the basics of pressure.
Absolutely. Pressure is really like the heart of everything
Yeah.
when we talk about how fluids behave.
Okay, so when we talk about pressure,
Yeah.
what exactly are we talking about?
So pressure is the force that a fluid exerts on a surface
Okay.
per unit area.
Yeah.
And we need to be really clear about the difference between gauge pressure and absolute pressure.
Okay. Gauge versus absolute. What's the difference?
So think about when you inflate your car tires.
Yeah.
The pressure gauge, right, that you use,
Yeah.
that's telling you the gauge pressure.
Okay.
It's the pressure above atmospheric pressure.
It's like relative to
It's-
the air around us.
But the absolute pressure inside the tire is actually higher
Okay.
because it includes that atmospheric pressure as well.
Oh, so there's always that extra pressure that we don't even think about.
Right, it's like this invisible force
Yeah.
constantly pushing on everything.
It's kind of wild to think about that.
It is. And it's really important to remember, units matter
Oh, yeah.
when it comes to pressure. Remember that Mars Climate Orbiter mishap?
Oh, yeah. Wasn't that a
Yeah,
big deal?
big problem. One engineering team was using metric units, so pascals,
Okay.
for pressure, and another team was using imperial units, pounds per square inch.
Oh, so they weren't speaking the same language.
Exactly. And the spacecraft ended up crashing
Oh, wow.
because of that unit mix-up.
Yeah, that's a cautionary tale for sure.
Absolutely.
Units matter.
Units matter.
So we've got pressure figured out,
Okay.
but how does it actually change within a
Mhm.
fluid?
Okay, so that's where Pascal's law comes in. It states that pressure at any point in a static fluid, so a fluid that's not moving,
Right.
is the same in all directions.
Yeah.
So the deeper you go,
Right.
the more fluid there is above you pushing down.
Right.
And that causes the pressure to increase.
So even if I turn my head sideways underwater,
Yeah.
it's the same pressure on my ears as if I was facing straight up.
Exactly. Think about it this way. Imagine two containers.
Okay.
They're connected at the bottom. One's tall and narrow,
Okay.
the other's wide and shallow.
Mm-hmm.
If you fill them with the same fluid
Okay.
to the same height,
Okay.
the pressure at the bottom
Okay.
of both containers will be identical.
Wait, really?
Yeah.
That seems counterintuitive. I would think the tall, narrow one, there's more fluid above.
So there'd be more pressure, right?
It's a common misconception. But Pascal's law tells us that the shape of the container
Oh, interesting.
doesn't matter. It's purely a function of the height.
So just the height
Just the height.
of the fluid column above that point. We call this the pressure head.
The pressure head. Okay. My mind is officially blown. So pressure increases with depth, but how do we actually measure this?
Right. So we have a whole range of tools from very simple to super sophisticated. The simplest is a piezometer tube.
Okay.
Basically, it's just a vertical tube that's open at the top,
Okay.
and it's connected to the fluid you want to measure.
Okay.
The height of the fluid in the tube tells you the pressure.
Oh, so it's like those old school blood pressure cuffs.
Yeah, exactly like that.
With the mercury.
Right.
I imagine like those simple tubes, though, aren't always practical
No, you're right.
or sensitive enough.
Yeah, for small pressure differences,
Yeah.
or if you're working with different fluids, we use something called a U-tube manometer.
A U-tube.
It's basically a piezometer tube, but it's bent into a U shape.
Okay.
The difference in the fluid heights between the two arms of the U tells you the pressure difference.
So you can choose the right fluid for your manometer.
Exactly.
And that way you can kind of control the sensitivity.
Exactly.
Okay.
But manometers do have their limitations, especially in really dynamic systems
Right.
or really harsh environments.
Yeah.
That's where we start using mechanical gauges, things like a Borden gauge.
Okay.
Those have a curved tube
Yeah.
that straightens out as the pressure increases.
Okay.
And then, of course, there are electronic pressure transducers,
Yeah, that makes sense.
which convert the pressure changes into electrical signals.
Like the tire pressure monitoring system in my car.
Precisely.
Yeah.
That's a great example. Think about it. Designing a sensor
Yeah.
that's accurate and durable
Tiny.
and tiny enough to fit inside a tire, that's a big engineering challenge.
Yeah, that's a good point.
But it all comes down to applying these basic principles.
Okay, so we've got like pressure, the basics down.
Right.
Now I want to talk about hydrostatic forces.
Okay.
These are forces that fluids exert on surfaces.
Mhm.
That's where like the visuals in my head start working. Like, why are dams shaped the way they are? Or
Yeah.
what keeps a giant ship from sinking?
Right. So all of those questions come down to this principle of hydrostatic forces. When a surface is submerged in a fluid,
Oh.
the fluid exerts a force on that surface because of the pressure we've been talking about.
So the deeper it is, the more force.
Exactly. The deeper the surface is submerged, the greater the force because the pressure is higher.
That makes sense.
Now, calculating those forces for plane or flat surfaces
Okay.
is pretty straightforward.
Okay.
For a horizontal surface, like the bottom of a tank,
Okay.
the pressure is uniform.
Right.
So the force is just the pressure multiplied by the area.
Easy enough.
But for a vertical or inclined surface, like the side of the swimming pool,
Yeah. Well,
the pressure changes with depth.
okay.
So we need to take that into account.
Right, because at the bottom of the pool wall, there's more
Yeah.
pressure than at the top.
Exactly. And to calculate the total force on that wall, we need to integrate the pressure distribution over the entire surface.
Okay, that sounds a bit complicated.
It can be, but there's a really cool visual tool
Okay.
called the pressure prism
Pressure prism, okay.
that makes it much easier to understand.
Okay, so what is a pressure prism?
Imagine a three-dimensional wedge,
Yeah.
right? And the base of that wedge is the submerged surface.
Okay.
And the height at each point represents the pressure at that point.
Okay.
The volume of this wedge represents the magnitude of the resultant force
Oh, interesting.
acting on the surface.
Okay, so for a rectangular wall,
Yeah,
it would look like a wedge
exactly.
with a triangle, like cross-section.
Exactly.
Okay.
And the location where that force acts is called the center of pressure.
Center of pressure.
And for a rectangular wall, it's 1/3 of the way up from the bottom.
So it's not right in the middle.
It's not in the middle. It's a little bit lower.
Okay, interesting. So the deeper it is, the closer it gets
Exactly. Yeah.
to the center.
Exactly.
Okay, that's cool. But what about curved surfaces, like the hull of a ship?
Right. So for curved surfaces, things get a little bit more challenging.
Yeah, I can imagine.
But we can still analyze them.
Okay.
We have to break down the problem.
Okay.
We consider the equilibrium of a volume of fluid that's enclosed by the curved surface.
Okay.
We can calculate the horizontal and vertical forces on that volume,
Okay.
which we know how to do because those act on flat surfaces.
Right.
Then the horizontal and vertical components of the force on the curved surface, they have to balance those other forces for the volume of water to be in equilibrium.
So we use what we know about flat surfaces to
Exactly.
figure out the curved ones.
Exactly.
Okay, that's pretty clever.
Yeah. And this approach is used for tanks under pressure too.
Oh, okay.
Although in those cases, the weight of the fluid inside the tank, it's often negligible
Right.
compared to the pressure forces,
Especially if it's gas. Right.
especially if it's gas. Exactly.
That makes sense. Okay, I think I've wrapped my head around hydrostatic forces.
Okay.
Now, I really want to dive into something
Yeah.
that's always kind of intrigued me, which is buoyancy. What makes some things float?
Yeah, buoyancy. Now,
Others sink.
it's all about Archimedes' principle.
Okay, break it down for me. What is that?
So Archimedes' principle states that the buoyant force on an object submerged in a fluid
Okay.
is equal to the weight of the fluid displaced by the object.
So if an object displaces, let's say, 1 cubic foot of water,
Yeah.
which weighs like 62.4 pounds,
Right.
the buoyant force acting on that object would be 62.4 pounds.
You got it.
Okay, and this applies
Yes.
whether it's fully submerged or floating.
That's right.
I'm starting to see how this connects to floating, right? If the buoyant force is greater than the object's weight, it floats. If the weight is greater, it sinks.
Exactly. A ship floats because it displaces a volume of water that weighs the same as the ship itself.
Oh, that makes sense. So it's all about the shape of the hull, like how much water it can push aside.
Exactly.
This explains how a concrete canoe can float. If the canoe is shaped to displace enough water,
Right.
the buoyant force is going to be greater than the weight of the concrete.
Precisely. It's a great example of how, understanding buoyancy
Yeah.
can lead to some pretty counterintuitive engineering feats.
It really is. Okay, we've got the buoyant force, but what about stability?
Stability.
I mean, a boat can float, but it can also tip over.
Right.
So how do we know if something's going to stay upright?
That's a great question. And that's where the concept of stability comes in.
I have a feeling this
Uh,
is where things get a little more complicated.
It does add another layer of complexity, yeah.
Okay.
But it's still based on the principles we've been talking about.
Okay, I'm ready. Where do we start?
Okay, let's start with the simplest case. A completely submerged object, like a submarine.
Okay, our trusty submarine.
For those objects, stability depends on the relative positions of the center of gravity and the center of buoyancy.
Okay, so the center of gravity is like where the object's weight is concentrated.
Yeah,
And the center of buoyancy is the centroid of the displaced volume.
You got it. Now, if the center of gravity is below the center of buoyancy,
Okay.
the object is inherently stable.
Okay.
If you tilt it slightly, the buoyant force and the object's weight, they create a couple that rotates it back upright.
So it's like a pendulum.
Yes.
Right. If the weight is below the pivot point, it always swings back to its equilibrium.
A perfect analogy.
Okay.
But if the center of gravity is above the center of buoyancy,
Okay.
the opposite happens.
Okay.
It wants to tip over.
Got it.
Yeah.
So for submerged object, it's all about the relative positions of those 2 points.
Exactly.
But what about floating objects where only part of the object is submerged?
Right. So with floating objects,
Okay.
things get a little bit more complicated
Yeah, I can imagine.
because the shape of the submerged part, and therefore the location of the center of buoyancy,
Okay.
can change as the object rotates.
Oh, so it's not fixed. It's
Yeah.
like moving around depending on how the object's tilted.
Exactly. And this is where the shape of the object
Yeah.
becomes really important.
Okay, I need a visual. Give me an example.
All right. So imagine a barge.
Okay.
They have a wide, flat bottom.
Yeah.
Even though the center of gravity is above its center of buoyancy,
Okay.
it's very stable.
Okay.
Why? Because as the barge tilts,
Okay.
the shape of that submerged part of the hull changes,
Okay.
and it shifts the center of buoyancy outward.
Oh, so the center of buoyancy is moving
Yeah.
in a way that's counteracting the tilting.
Exactly.
So it wants to come back up.
It creates a righting moment.
Okay, cool.
But a tall, slender object, like a sailboat,
Okay.
is much less stable because a small tilt
Right.
can cause that center of buoyancy to shift
Yeah.
in a way that makes it tip over more.
Oh,
So
so it amplifies it. That.
Exactly.
Okay. This is really interesting. It's like a delicate dance between the weight,
Yes.
the shape,
Absolutely.
and that center of buoyancy.
Yeah.
So we've been focusing on fluids at rest,
Right.
but what happens when they start moving?
That's where we enter the world of fluid dynamics.